Good morning. Let's pick up where we left off with chapter 18. We were taking a look at distributions of molecular speeds, and we went into quite a bit of detail there. What we want to do now is we want to move on and take a look at different representations, keeping track of the pressure, the volume, the temperature, number of particles, primarily in gases. So we're going to be using the ideal gas law. We'll talk some about liquids and solids along the way. But first of all, just to kind of orient ourselves, let's say that we have a container with some gas molecules. And what we want to do is we're going to put the container in a constant temperature environment, and then we're going to make sure that the container conducts heat reasonably well. So what will happen then is that the temperature of the gas molecules of our sample inside are going to be maintained at a constant value due to the fact that they are in thermal equilibrium with the container and with the surroundings. So what we're going to ask then is, if the temperature stays constant, how are pressure and volume going to be related? And not just temperature staying constant, but also the number of molecules. So if I take a sample with a fixed number of molecules, and we set the system up in a way where the temperature will stay the same for the sample, what the ideal gas model predicts is, well, first of all, PV equals NKT. If N is staying constant, and T is staying constant, well, little k is a constant, it's Boltzmann's constant. What we're saying then is that P times V is going to remain a constant. And that says if we do some kind of a graph, that P is going to be inversely proportional to V. So pressure and volume are going to be inversely proportional. Now, I don't know if you remember from your algebra classes or your analytic geometry classes, but formulas of that form are hyperbolas. Now they're hyperbolas that fit within one quadrant. So that's like y is equal to 1 over x, or a constant over x. So what happens is, anytime we keep the temperature constant, what we'll do is we'll have a hyperbolic contour where all the points along there correspond to the same temperature. Now, as the volume gets less, the pressure goes up. And then as the volume increases, the pressure goes down, is the way that's going to work. So let's think about this. What does keeping the gas molecules at the same temperature really mean? Well, if they're at the same temperature, we'll have the same distribution of speeds. So we'll have the same distribution of kinetic energies. And if we pack them into a smaller region, then they're going to be bouncing off the walls more frequently. And that means that the pressure is going to go up. If we increase the volume, then they're going to be bouncing off the walls less frequently, so that means that the pressure goes down. Now, we don't have to just consider the walls. The pressure is a property that exists throughout the sample. So if I put an object inside, let's drop something down inside our container, that object is also going to experience pressure due to all of the collisions with gas molecules. So it's a property throughout the sample. So what we can do then is, let's set up a 200 Kelvin isotherm, and then let's increase the temperature to 400, 600, 800. So I set up a series of these isotherms, or contours of constant temperature. So, if I've got a gas sample and it's at a fixed temperature, there's still this flexibility in terms of volume and pressure. Okay, so those are some remaining variables that are going on. Now, we're going to be analyzing a lot of different processes using these PV diagrams. So it's going to be handy for us to realize that with the ideal gases, there's always going to be these hyperbolic contours of temperature, of constant temperature. So that says if I've got something where the volume's going up, the pressure is being maintained, it must be the case that the temperature is also going up. Increasing temperatures are in that direction, decreasing temperatures are in the opposite direction. Now, when we look at gases, we've been saying that, in the ideal gas molecule, everything behaves the way we just looked at the previous slide. But it turns out that in real situations with real gases, there are changes of phase. If the temperature drops or if the pressure increases, there's the possibility of undergoing a phase change. That collection of molecules that is in a gas phase, it could become a liquid or it could become a solid depending on what's happening with the pressures and the temperatures. So here's the very same PV diagram, but this time we're thinking in terms of a more realistic, a more complete description of how gases are going to behave, allowing for phase changes. So what happens here is, if you remember that previous one, we had these different isotherms mapped out. And what this is saying is, look, as long as the temperature stays high enough, as long as we're at temperature A, whatever that corresponds to, that says that yes, we will have, the sample will remain a gas. It doesn't quite behave like the hyperbolic. Once you pack these into a small enough region, pressure goes up, volume decreases, the gas molecules actually do interact with each other, but a small amount. If we pack them into a smaller region, those interactions are more frequent, and the stickiness between molecules becomes more and more of an effect. So we don't have those nice, idealized hyperbolic contours, and we can see that A now looks like this instead of A prime, which was the ideal situation. If we drop in temperature and do the same thing, we find that in this situation, those intermolecular forces become more important. So as we lower the temperature, the molecules are not moving as fast, and when they do bounce off each other, the stickiness has a bigger effect. Now, once we drop below what's called the critical point, or the critical temperature, what they're referring to as point C here, we now have the possibility that the gas could become liquid. So above a certain temperature, there's no phase change between liquids and gases. So liquids and gases don't separate into distinct phases. Now we're used to that, right? If I have a sample of liquid water sitting there, we know that some of the molecules are always going to vapor. It's kind of an equilibrium that gets set up between the two. But if I go to a high enough temperature, that doesn't happen. Instead, as I make the gas more and more dense, at some point it just looks more like liquid than it does a gas. But there was no distinct phase change that took place. So that's kind of an interesting... Phase changes are actually... There's a good deal of complexity to that. We tend to think in terms of gases and liquids and solids. If we go to really high temperature, they're plasmas. But there are actually more subcategories of these phases, and for better or worse, we're not going to spend a lot of time looking at these, but we do want you guys to be aware of their existence. So this is our first kind of example. Now as we drop even farther in temperature, what we find is that there's a phase change that takes place here. Right? This time when we compress the gas, we see condensation begins to take place. If we're at a low enough temperature, those gas molecules are brought close enough together, they actually stick together and form liquid. So again, the common example of this is water, right? If we have, let's say in the evening, late evening, there's a bunch of water vapor in the air, in the gas form. As the temperatures drop, and we drop down to these lower contours, what will happen then is that we'll end up with condensation. So individual molecules begin to stick to each other and form droplets. and then those droplets tend to get larger and larger. We'll have a phase transition that takes place, and that's what this boundary represents. So this is the liquid vapor transition point, and here, as we decrease the volume, we're going to drive more and more of that gas into liquid phase. And by the time we come out the other side, it's going to be entirely liquid. So at these lower temperatures, there is a distinct phase transition where both phases coexist. And then once we get to a small enough volume, we're back to 100% liquid. Now what this graph's leaving off is it's leaving off all the solid regions. So it's not this simple. This is just showing gases and liquids. So there's greater complexity than this too. So what I did is I went online and looked up a fully three-dimensional phase surface. So this, instead of just having pressure and volume as the two axes, there is also an axis that shows temperature. Now you may have seen these in physical science classes or chemistry classes that you've taken. You can go online and look these up. They're actually three-dimensional objects, and they have these, this complex surface. And now what we're saying is, if we compare it with the graph we looked at before, at a high enough temperature, here's one of those isotherms, at a high enough temperature we go from vapor that gets denser and denser, we skip the phase transitions, and as it gets denser and denser, it just starts to look more like liquid. Again, if you think of that fog formation on a cold evening or a cold night, and then as the fog gets thicker and thicker, it just feels like we've gone from vapor into something that's soupy, something that's kind of liquid. That's what's happening here with no distinct phase transitions. If we drop to a lower temperature, what we find is that there are distinct phases, liquid and vapor, and if we continue to compress, we go to 100% liquid. Now what this diagram is keeping track of, which the last one didn't, is it's got the solid regions filled in. So once you go to high enough or small enough volumes, or as you drop in temperature, as you drop to lower and lower temperatures, what happens is you have these solid regions. So this now is solid. Once we get down to low enough temperatures, we'll run into these solid regions. Similarly, with this liquid and vapor state, if we drop in temperature, that's going to go into a solid and vapor state. So another interesting feature of these diagrams is, we said above a certain temperature and pressure, there's really no distinct phase difference between liquids and vapors. One is just a denser version of the other one. What also happens is if we drop below a minimum pressure, there's no such thing as liquid. For whatever compound we're looking at, if we drop below a critical pressure value, the liquid phase ceases to exist. So kind of an interesting property of these different materials. All right, so I included a table here. This is talking about changes of phase, critical temperatures and pressures. And so what we're saying is if the temperature is above a certain critical temperature, or if the pressure is above a certain critical pressure, there is no gradual transition of gas into liquid. It's just variations in density between, there's no distinction between those phases. And so for water, that's at 374 Celsius is where that happens, or at a pressure greater than 218. So these are some pretty high values. And then carbon dioxide, oxygen, nitrogen. So you can kind of look and see all of these are requiring pretty high pressure to make that happen. Helium's the only one, at 2.3 atmospheres. That's enough pressure for helium that the helium would just go from vapor, denser and denser vapor, until at some point you go, it just looks like a liquid to me. something to be aware of. Here is a phase diagram. Now this is showing some different axes. Pressure is on the vertical axis, but notice that we've switched to temperature. So what it's doing, what these diagrams are doing, I'm going to go back and just restate this. These are the general phase surfaces. So to show all the regions of different phases and phase combinations, you really need to work in 3 dimensions. What they're doing with these other phase diagrams we're looking at is either taking a projection of pressure and volume or a projection of pressure and temperature. Okay. And again, these are fairly complicated, so mostly we're just saying, hey, be aware of the effects of different phase changes. So here's a P versus T graph, and so we don't have volume listed here, but again, what we're showing is that there's a critical point. There is a boundary between liquid and vapor up to a certain critical pressure and temperature, and beyond that, gas and liquid become different versions of the same thing. Traveling through these temperatures and pressures, we see distinct gas to liquid behavior. If we circulate around that, we don't see it. Another thing to realize on most of these phase diagrams is to get a reasonable looking phase diagram, they tend not to use linear scaling on the axes. So if you'll notice the pressure here, you know, this is 1 atmosphere, here's 218. This doesn't look like 218 times as large as this, and then this is 0.006. It's very common to see these as logarithmic axes, but I don't even think this one's logarithmic. And then the lower scale here is in Celsius, which confuses things. You know, putting it in kelvins would probably make more sense. But this is for water. And so here is the vapor to liquid boundary. So liquid to vapor, that would be when it's boiling. Over here we have solid to liquid. This is the melting boundary between those 2 phases. And then here we have sublimation. We have solid going directly to vapor, skipping the pressure entirely. Now, what this is showing is that water does not exist as a liquid if we drop below 0.006 atmospheres. And you're thinking, well, that's no big deal, right? Earth has plenty of atmospheric pressure to make sure that water can exist as a liquid. But what about Mars? So, you know, we've been sending all of these rovers to Mars, all of these spacecraft, to go up and analyze what's going on Mars, and now we've established that there's solid water, there's ice. If these rovers dig a little bit down into the soil, they can find, or down into the dirt, what they've shown is that they can find solid water. So are these ice crystals of water. Now what happens with that water is because the atmospheric pressure on Mars is so low, water can't exist as a liquid. So instead of going through a liquid phase, it just vaporizes into vapor. Goes back and forth between vapor and solid. When it freezes, again, if the temperature drops, and then you've got vapor dropping back down into solid. So earlier in Mars history, you know, hundreds of millions or billions of years ago, Mars had a lot more atmosphere, and the atmospheric pressure would have been much higher, and Mars would have had liquid water. So we have all that evidence. It looks like what were riverbeds or lakes of water that existed on Mars, and it's all gone now. And that's due to Mars' size. Mars' mass is much less than Earth, something like 1/10 the mass of Earth. The gravitational fields are much less, and they're not as able to hold on to atmosphere. So over time, Mars has lost most of its atmosphere, and as a result, atmospheric pressures are low enough, liquid water doesn't exist. Okay, at least not in equilibrium. Here's another phase diagram for, this one is for carbon dioxide. Now this might be familiar. A lot of you are probably aware that carbon dioxide, if you get solid carbon dioxide, which is known as dry ice, that dry ice, which is used as a coolant, right? Sometimes you'll get packages of meat, for example, shipped with dry ice in there to keep it cold. And what happens with the dry ice is when the ice raises in temperature, it undergoes a phase change. And that phase change is from solid directly into vapor. So that makes carbon dioxide very useful as a coolant, because you're not going to get all drippy from liquid carbon dioxide. Now, does carbon dioxide ever exist as a liquid? That's a good question, and it does. Carbon dioxide exists as a liquid, but only if the pressure is at least 5.11 atmospheres. So we need something greater than 5.1 atmospheres in order to see liquid carbon dioxide. So if you've got a planet where the atmospheric pressure is much higher, Venus would be an example, you could have lakes of carbon dioxide. Now the temperatures too, we're going to have to be careful about what the limits are of temperature. And what we're finding here is the critical point for CO2 is at 31 degrees Celsius. And temperatures on Venus are in the hundreds of Celsius. So we're not going to have puddles of, at least not in this liquid phase the way we have it outlined here. So anyway, it's kind of interesting that different phases, liquids or solid phases, only exist within certain ranges of temperatures or certain ranges of pressures. Liquids in particular only exist within a range of temperatures and pressures. Here is a container. So here we are looking at a container, and I guess they're saying it's water. Again, water is so familiar, that's handy to work from. So what we've got here is we've got a container of water. If it's open, the water can just evaporate. So that means that individual molecules could separate out. Now that's not the same thing as boiling. Boiling is, and we'll see this, boiling is a situation where the liquid and the vapor are coexisting. Evaporation is not like that. Evaporation, the water molecules separate, but then the water molecules leave. So it's not under an equilibrium closed condition. In evaporation, it's the fastest molecules that are leaving, and so the remaining water that's left behind, ends up dropping in temperature. Okay. Now the reverse of this is condensation, and they're just pointing out. Now another thing to keep in mind here, let's say we have a container with water. The question becomes, is there air inside that container? So when I close it off, have I enclosed air inside there to maintain pressure? Or the other possibility is to fill the container with only water molecules. Don't put anything else, no air, no nitrogen, no oxygen, just water molecules alone. That's going to make a difference on what the pressure is set up, the vapor pressure of the water molecules inside. And that'll make a difference as to whether there's enough pressure for the water to remain in liquid form. So here is vapor pressure and humidity chart. And what this is showing is, for a particular temperature, how much pressure is there of the water molecules up above that liquid. And so you can see, as you go from lower temperatures to higher and higher temperatures, what's happening is the vapor pressure is going up. And that says that as the water molecules have more kinetic energy to them, it's more likely they will leave the liquid and form a vapor in equilibrium with that liquid. Now, what's interesting on this chart here, I guess, is that by the time you've reached water at a temperature of 100 Celsius, which would be boiling, it says at a temperature of 100 Celsius, the pressure due to water vapor is now 101,000 pascals. It's equal to atmospheric pressure. So at 100 Celsius, water vapor bubbles form within the water itself, and they have a high enough pressure to them that they're self-sustaining. So at 100 Celsius, we do have the phase transition from liquid to vapor, and that's because you've reached a point where the formation of vapor is stable. Not just evaporation from the surface, but the formation of vapor bubbles actually creates bubbles with enough pressure to hold their own against the surrounding liquid. Now, let's take a look at this next diagram here. So this is showing water actually boiling or undergoing a vaporization process. So we're heating this water. The water here would be at 100 Celsius. And once you get to 100 Celsius, like we were saying with the previous slide, you're now going to get formation of vapor bubbles. The pressure inside there, due to those water molecules, is now 1 atmosphere. Now the pressure, certainly at the surface, as we drop down not too far, the pressure in this region is going to be about 1 atmosphere of pressure. Think back to fluids chapter 11. So the pressure in this region is going to be somewhere around 1 atmosphere. And these vapor bubbles that are forming are able to hold their own. They're able to form and maintain enough pressure that they survive. Now, due to gravitational effects, they're going to make their way to the top. But these bubbles of vapor that are forming are sustainable. So the phase change, liquid boils, when the saturated vapor pressure equals the external pressure. So now these bubbles can push the liquid out of the way and remain as vapor. So how does this figure in with this idea of humidity? So when we have water open to the atmosphere, the water is under a pressure of 1 atmosphere because of the air. But the partial pressure of the water vapor is less. So it's not the water molecules that are maintaining that 1 atmosphere of pressure, it's the other air molecules that are performing that effect. So what happens is, when we have water open to the liquid water open to the atmosphere, some portion of those water molecules will evaporate and go into the air. At some point, the air can become saturated with water molecules. What saturation means is there is an equal rate of water molecules returning to the liquid from the vapor back to the liquid as there are leaving the liquid going into the vapor phase. So once there's an equilibrium process between water molecules going vapor and vapor molecules returning back to liquid, that's saturated vapor pressure. And those are the numbers we were seeing in those previous tables. Now, relative humidity says how many water molecules are currently in the air in proportion to how many water molecules would there be if the air were saturated with water. So as long as you're below 100% relative humidity, then water molecules, on average, will evaporate and leave and go into the atmosphere. Once you hit 100% humidity, then there's an equilibrium set up between the two different directions. And that's how we keep track of humidity, right? If we're listening to a weather report, they're going to say we're at 60% humidity or 35% humidity or 99% humidity, and that's a comparison between what portion of the molecules in the air are water versus what would be the saturated vapor pressure of water molecules. So partial pressure divided by saturated pressure for the temperature outside. Now that's going to change with temperature, the saturated number. All right, so let's do a relative humidity calculation here. It says this, it says that on a particularly hot day, the temperature is 30 Celsius, and the partial pressure of water vapor in the air is 21.0 torr. What is the relative humidity for this? So let's see what they're actually showing us here. Let me go back to the table. So I'm going to come back to here. So they're saying in this example that we are at a temperature of 30 Celsius. And so at 30 Celsius, if it were just the water molecules themselves reaching equilibrium, we would expect at 30 Celsius 4,240 pascals of pressure due to the water molecules themselves. That would be the partial pressure. Now, I guess I have issues with this unit of torr, or millimeters of mercury. I wish we would phase this out. I always feel like millimeters of mercury are kind of archaic. We have these other pressure units. We have pressure units of atmospheres. We have pressure units of Newton per square meter. For better or worse, I'm going to say for worse, we have retained this millimeters of mercury unit. And of course, as you know from doctor visits, blood pressure and such are given in millimeters of mercury. I, for one, would vote in favor of switching everything over into standard units into pascals. If you notice on automobile tires, for example, automobile tires now are rated in pascals or kilopascals, which I think is a step forward in simplifying the way that we keep track of these things. All right, so here we are with this problem that they've given us. So the temperature outside is 30 Celsius. And so at 30 Celsius, here's a container of water. Here are the water vapor molecules that are in the air on that particular day. Now, at 30 degrees Celsius, water vapor pressure in equilibrium would be 4,240 newtons per square meter. We just got that off that table. And so looking at the table, it says at equilibrium, that would be the partial pressure. Now what we find though is that when we actually look to see what the water vapor amount is in the air that day, we find that it's at 21 torr. Now again, I don't care for torr. Let's see how we can get rid of those units. 1 atmosphere is 760 torr, 760 millimeters of mercury, and that's the same thing as 101,300 pascals. So the conversion here apparently is each torr is like 133.3 pascals of pressure. So we can take that 21 torr that we were given and use this conversion factor. 21 torr would be the equivalent of 2,800 pascals, or 2,800 newtons per square meter. Okay, so relative humidity would come down to this. At this temperature, in equilibrium, what would be the pressure of water vapor? And the water vapor pressure would be 4,240. What's the actual reading and the actual reading is 2,800. So currently, if, looking at the number of water molecules in the air, according to this problem, we are only at 66% of saturation. And that says that if we have, water lying around in puddles, we will continue to see evaporation take place. The direction of phase change would be having more of the liquid go into vapor. Okay, so that's an example of relative humidity. And if this were allowed to continue, the relative humidity, more and more water evaporating, the relative humidity would steadily go up until it reached 4,240. At that point, we would be at 100% of relative humidity, and there we would have an equilibrium between the water vapor in the air and the liquid water, everything being at 30 degrees Celsius. I guess I needed a Celsius on this. Add a capital C right there. All right, so that's relative humidity calculation. So now in the weather forecast, you can think about, oh, that's what relative humidity is referring to. And this is just more of the same, I guess. What it's showing here is that when the humidity is high, it feels damp, it feels muggy, and it's very hard for water to evaporate. Now, a lot of our cooling, if we're out being very active, and especially if the temperature outside is pretty high, then we really depend on evaporation of water off our surface. We sweat, and that water evaporates, and that helps keep us cool. And if the humidity is really high, it makes this evaporation process less likely. So it's harder to stay cool. People say, if you go to Arizona or something, sure, it gets to be 100 or 110 Fahrenheit, but it's a dry heat, meaning that, sure, the temperature is really high, but you can still easily evaporate water off your skin. The process of sweating and evaporating water works really well in that dry environment. So here what we're seeing, this is morning fog, and what happens here is, how do we get all this condensation during the nighttime? Well, during night, the temperature of the air drops down. As the air temperature drops, the water vapor saturated pressure decreases. Air just doesn't hold as much water at lower temperatures. So some of that water vapor is going to condense out of the air. And so you end up with something like fog. And if you've got fog formation, then in the region where the fog formation has taken place, the air's kind of at 100% relative humidity. It's got all the air molecules that will fit in that air at that temperature. And so you're getting any excess water molecules condensing out. Here, what they're talking about, also vapor pressure and humidity. So here's a conceptual question that we are being asked. Why is it during the winter, which we really don't have here very much, temperature really getting cold outside, why is it that in the heated buildings they feel so, seem to be very dry? And so what's happening here is if we're taking air with a reasonable amount of water in it, but at a low temperature, and heating it up, well, now the air could be holding a lot more water. And so just simply by heating the air, the relative humidity will drop substantially. And that's what we have happening. The air inside buildings can seem very dry because we're taking colder air, heating it up, and even though the amount of water hasn't changed, the relative humidity has dropped considerably. So it feels much drier. All right, when we looked at gas molecules, when we came up with our derivation for the ideal gas law, something that we had suggested was that these gas molecules could be thought of as if they don't take up any space. So all of the volume is available to every gas molecule. And the argument behind it is, you know, the molecules are so small, typically for the space that we have available to them, that the size of the molecules is negligible. But that's not a completely good approximation, especially if we go to higher densities or higher pressures. It could be that at some point the space, the volume that the gas molecules themselves are taking up start to become kind of significant. So the van der Waals equation of state, it's a better representation of how gases really behave. So that ideal gas formula is a great idealized formula that we come back to all the time, but in reality, it can be off, you know, by, I think we said that within 1%. It's going to get numbers within 1% or so most of the time under the conditions we look at. But if we want to go to higher levels of precision, we have to take into account the fact that, well, the picture here is showing that when we have collisions between atoms or molecules, the size changes the way that that collision takes place. There is an excluded volume of those gas molecules. So how did van der Waals change the ideal gas law to try and adapt to these properties? So what happens here is, first of all, instead of just having P times V over here on the left side divided by N, what we've got is we've got a reduced volume. Now they've taken the little n and brought it over to the left side, and that confuses things a bit. But bringing that the n over to the other side gives us a volume per mole, which is referred to as the molar volume. And the molar volume is going to get reduced by some amount. And that depends on what the species of the gas is. So we're not going to look at the van der Waals formula in detail. So it's really, again, something we want you guys to be aware of, that the ideal gas law is not ultimately 100% precise. That we can do better by going back and complicating the formulas. So if you look up these coefficients A and B for different gases, you can see how much of an excluded volume they have. Now what we also end up with is we have a surface effect, a wall effect, that applies to the pressure. So we end up with this pressure effect where the pressures that we're measuring also, because of the finite size of the molecules, is not quite the pressure that we would have if the gas molecules were just little point objects. So by making these changes, we can get a better fit between what we actually measure in terms of properties of gas molecules and this formula. So this formula allows us to go in and get better predictions as to what the gases will behave like. So going back to these PV diagrams that we looked at earlier, what the van der Waals formula will do is it will take us away from these hyperbola, which we said the ideal gas model was predicting perfect hyperbola at whatever temperatures. What the van der Waals formula does is it begins to show this disruption created by intermolecular forces and by the excluded volumes due to the size of the gas molecules themselves. And so that more complicated formula will give us this curved effect. Now remember, the area inside this dashed line here, that's actually when we're undergoing a phase transition. So that's not taken care of with the, we're not trying to predict that effect with the van der Waals equation. What we are trying to do is get the approaching curve coming into that phase change to better represent what we observe in the lab. Okay. So just to be aware, there are greater complexities than what we've allowed for. Now, here's another sort of interesting topic here, and that is what we refer to as the mean-free path. Mean here meaning the average distance. So if I have a collection of gas molecules in the air, for example, we could run some numbers. In fact, we will run some numbers and see how this, what kind of predictions this makes for air molecules in the room. Let's say that we haven't, we follow one of the air molecules in the room, a nitrogen or an oxygen molecule, and we just follow all the collisions that it has. Now, what we would expect is the distance it travels between collisions varies from one collision to the next. Well, on average, if we took all of those distances between collisions and average them, what would we find? And so we can do calculations of mean-free path. Now, we're not going to go into the details of this either. You may be getting the idea here in chapter 18 that there's a number of items we just want you to understand conceptually. We really aren't going to be looking at detailed problems. And the best way you can determine, you know, what level am I supposed to understand, what numerical skills, problem setup and problem calculation skills should you have, take a look at the homework list. So if you take a look at the homework list, and if you can do the problems that are listed in the homework, you're fine. You're going to be fine with the course. Now, let's be clear about what that means. Sometimes students go, oh, if I can solve specifically the homework problems, I don't have to be able to solve any other problems. That's not true. What you do have to be able to solve is any problem, or what you want to be able to solve, are any problems that are kind of at the same conceptual level. So once you're looking at the homework problems from this chapter, from chapter 17, future chapters, what you want to ask yourself is, okay, I understand how to solve that problem. How could a similar problem be set up? You know, how could I change this problem around so that I'm asking the question a little differently? Or what's kind of the same skill level? If I start from the same set of concepts, what additional sorts of problems could I solve? So you're certainly trying to pick up broad, flexible skills that can apply to a number of problems. So when you go through the homework and you kind of see the list of problems that are there, look for other problems, maybe not listed in the homework itself, but look at other problems in the textbook that sound pretty similar. If it sounds similar, you probably should be able to solve those problems too. Okay. Now with the mean-free path, all we're going to do is, well, we've already got this picture that we have here. We'll look at a couple more diagrams to kind of get an idea of what's going on. But then we're just going to put out the formula. And so any problem in the homework or on exam with mean-free path it would be a plug-in, okay? Which means that we may not see a problem like that, but you should at least be ready with that formula in your notes for, you know, if something showed up on homework or if something showed up on the midterm. So mean-free path, we're kind of getting a conceptual idea of what we're talking about here. So the derivation works something like this, and again, this is the formula that we've come up with. So as far as calculating the mean-free path for a molecule, what we need to know is how many molecules per volume do we have? So I want to be able to calculate number of molecules per volume for a particular situation. The more molecules per volume, that says that the mean-free path is going to be shorter, right? If the molecules are packed together more closely, I'm not going to be able to travel very far before I hit another molecule. So the derivation looks something like this. It says, look, here is some distance that I'm going to travel, and just statistically, what's the chance that there's going to be a molecule in my path? So if I think in terms of traveling some distance, what's the chance that that distance is free of any other molecules, and what's the probability that there's going to be another molecule within that volume? So as I'm making my way through here, if anything is filling that volume, if anything has found its way into the volume, there's a possibility that there's going to be a collision. In fact, there will be a collision for that case. Starting from that diagram, we can derive the formula that we see here. So let's just try this. Let's say that we're in the air and we're at STP, and again, I'm gonna cross out the STP. As you guys already know from class so far, from lectures, I feel like STP going at 0 Celsius, I don't want to do 0 Celsius because I'm not in rooms at 0 Celsius very often. I'm much more often in a room that's at 20 Celsius compared with 0. So, so let's take out the 0 Celsius and replace that with 20 Celsius. Now I'm going to go ahead and keep the 1 atmosphere of pressure. So 1 atmosphere of pressure, 20 Celsius as a temperature, and then the diameter of the O2 and the N2 molecules is, it's about 300 picometer. So, and I think we have talked about that too, you know, kind of what's the size of a molecule or an atom, and atoms and molecules tend to be a few hundred picometers in size. So let's see what this problem looks like once we get this thing set up. So here's the formula. This is telling me on average how far is an air molecule going to travel before it runs into another air molecule. And we're thinking in terms of O2 and N2. Now the temperature I'm going to use is 20 Celsius, which in terms of kelvins is going to be 293 kelvins. So what we needed to calculate, the formula is telling us, is how many molecules are there per volume. Now I can calculate the number of molecules per volume because I've got the ideal gas formula. And the ideal gas formula can be rearranged so that to show that N over V should be given by pressure, Boltzmann's constant, and temperature. So let's do that. I'm going to put in 1 atmosphere of pressure. I'm going to put in Boltzmann's constant. And then I'm going to put in 293 as a temperature. So now as the temperature goes up, the N per volume is going to go down. So as temperature goes up, we've got not as many molecules per cubic meter. And that means that the mean free path is going to get longer. And that's what's happening with the formula that we've got right here. All right, putting all these numbers in, I'm getting number of air molecules per volume to be 2.5 times 10 to the 25th molecules per cubic meter. Okay, so I'm going to go ahead and do everything in standard units here. I'm not quite sure how to judge what the mean free path might be, so I'm just going to do a calculation all in standard units, everything in meters, and then make adjustments at the end into something more intuitive. So the diameter they gave us was 300 picometers. And so what I'm going to do here, and again I could cross these things out. I'm not sure how those slipped in here. But number per volume was 2.5, 10 to the 25. The radius of these O2 and N2 molecules, we're going to estimate at 150 picometers. And pico is 10 to the minus 12. So that's what we're looking at. And then plugging all those numbers in ended up giving me a mean free path that's 1, actually came out 1.00, 10 to the minus 7 meters. Now that's kind of putting me in the range of nanometers, and so that's what I adjusted into. So a mean free path is about 100 nanometers. Now 100 nanometers would be 100,000 picometers. So let's think about that. If I've got 100,000 picometers between collisions, and the molecules themselves are like 300 picometers in size, what that's giving me is about 300 diameters between collisions. Let me check and see. I might be off by a factor of 10 on that. We've got 100,000 picometers, and we're dividing by 300. Yeah, I think that needs to be 30 diameters. I don't get 300 diameters. So I think we're looking at about 30 molecular diameters as we go from collision to collision on average. So, you know, if we think of the molecules as being this size, and we measure 30 of those, you know, something this size would go all the way across the room maybe, and then hit something else of this size. That would be like 30 diameters, something like that. So check that, double check that as far as 30 diameters versus 300. I'm leaning towards 30 diameters right now, but I will also go back and double check that number. Okay. So that's, you know, that gives you kind of a way to imagine what's going on with these air molecules. They're running into each other about this frequently in terms of distance. Now, a couple of the last sections in here, which we're really not going to look at in detail. Diffusion, just be aware of diffusion and how molecules make their way through a substance. Diffusion occurs from a region of higher concentration, and just like everything else that we're looking at in thermodynamics, this is all statistics driven, right? So what we're saying is if I start with a high concentration of molecules here, and they are making their way randomly, I mean, they're not intending to end up going any particular direction. But the fact that we have more molecules here means that when they all move sort of randomly, on average, what's going to happen is we're going to get more molecules in that middle region, and then more molecules in that region to the right. So just by random motion, mixing takes place, but the mixing takes time. So it's not going to happen immediately, but these concentration gradients will go away if given enough time due to diffusion effects. Now there's a formula with this. I'm not going to use any examples with this. It's up to you guys if you want to look at the formulas. What they've done is gone through and defined diffusion constants. And notice that the diffusion depends on the material we're looking at and the material that it's placed in. So it's not enough to know that it's oxygen that's diffusing. We have to know, is it diffusing through air or is it diffusing through water? And what this is saying is, if it's in air, it's diffusing, you know, 1,000,000 times faster than it is if it's dissolved in water. And so this does become important with a lot of, I'm sure in a lot of applications, but one of the applications here is separating out biological molecules, you know, large proteins or DNA, some of these really large molecules can be separated out using different types of media, different types of gels, and depending on what the size of these molecules are, they'll either move faster or slower through a particular medium. And so understanding this diffusion process and calibrating it allows us to determine the molecular mass, for example, of different compounds. You may have seen this in chemistry class, maybe in organic chemistry, using chromatography techniques, also as a way of looking at how fast materials move through a particular medium. Okay, so there is this last example. I'm not going to take a look at it. You guys are not responsible for it. It's looking at how long it would take for ammonia molecules to be detected 10 centimeters from a bottle after being opened. All right, summary of chapter 18. I think we've looked at all of the topics listed here. Again, those last couple of topics, the mean free path, we looked at an example of just plugging some numbers in, and then diffusion really just conceptually talked about diffusion. All right, so that wraps up chapter 18. So we're through 17, we're through 18. I don't know if I've told you guys this, but there is a lot of stuff in chapter 19. So 19, we'll start looking at that next time. Again, as always, if you've got any questions, let me know. Stop by office hours, and let's get whatever questions looked at and answered.